Our topic for today are combinations. This should seem very, very similar to the work we were doing in the last unit or the last lesson with permutations, because combinations and permutations have a lot in common. There are many things that are similar about them, but there is one really, really big difference. You will note, though, that the learning objectives are very similar to the learning objectives that we had for permutations. Number one, know what a combination is. Know how to recognize them. And the second learning objective, you should be able to calculate the number of combinations using a formula and using technology. Okay, so starting off, I'd like to consider this example. If you go up to Homesteader's Restaurant in Minot, they have a kiddie menu. And the kiddie menu actually has some pictures on it that little kids can use to color crayons. When you go there, they actually do have 5 different color crayons that they'll give out to kids. But they don't give out all 5 crayons to every single kid. They only give out 3 crayons. I'd like to ask you this question. If I'm going to give you 3 crayons so that you can color, does it matter which one you're given first? Like if you're given a blue, a yellow, and a pink crayon, is it important that you get the blue crayon first and the pink crayon third? Or would it be the same if you got yellow first, blue second, and pink third? These instances are considered the same. In this problem, the order in which you get the crayons does not matter. There's no first crayon, second crayon, third crayon. Just as long as you get picked, that's all you care about. And it doesn't matter if it's first or third. Problems like this, where the order is not important, are combination problems. This is the big difference between combinations versus permutations. When we were doing permutations, we said, yes, first, second, third is important, like a race. Here, the order is not important. When you're doing problems, you will have to ask yourself, is the order important? Whether it's yes or no will determine whether you do combinations or permutations. Continuing this crayon problem, here are the 5 crayons we have. There is orange, yellow, blue, green, and red. How many different groups? Or create a list of all the possible groups that you can have. So the colors we have, and I'm going to put them in alphabetical order. You have blue, green, orange, red, and yellow. The big gory. That looks weird. Alright, so let's get a group of 3 crayons. We could have blue, green, orange, and then get rid of the orange for the red. Get rid of the red for the yellow. You'll notice that these ones take care of everything with blue and green. If we have both blue and green, we've taken care of the other 3 options that might get paired with them. We could continue that then and saying, what about green with orange? That would give us green, orange, and red, green, orange, and yellow. But after we have orange, red, yellow, we could try going back to green, orange, blue. Why is green, orange, blue a problem? We already have it with blue, green, orange. We already have BOG, BOG. It's just in a different order. So this one we already have. We're not going to include it again. Well, now that we've done all the blues, all the greens, we'll start with an orange. Orange, red, yellow. Could we do anything else? Like orange, red, green. Orange, red, green is here. Orange, red, blue. Where is that one? Okay, so orange, red, blue we need. Could we go to orange? Okay, so we had orange, red, yellow, orange, red, blue, orange, red, green. Orange, red, green we already had, so it finishes that one. Next we can go on to red, yellow, red, yellow, blue. Do we have that one? Okay, so red, yellow, blue. What about red, yellow, green? We have that. The only other ones where we had red and yellow were red, yellow, orange. So we've got those. So right now we're looking at 1, 2, 3, 4, 5, 6, 7, 8, 9 answers right now. Do you think we've got them all? Well, this is a big part about it. Remember when we were doing permutations and we were doing the fundamental counting principle, how we were able to say, if you use the fundamental counting principle, it will tell you how many answers you're supposed to have. And you can use permutations to figure out how many answers you're supposed to have. We have the same thing with permutations. Right now, we're able to figure out 9 answers. Are we supposed to have more? That's what we can actually do. Since this is a combination problem, and I want to point out again, a combination is a grouping of objects where the order does not matter. All right, so continuing. You'll want to write this formula down. You remember how we had a permutation formula? This is the combination formula. You should note how very, very similar they are. When we had the permutation formula, NPR, that was n factorial over the difference. This is pretty similar. It's just an added component. Specifically, if we scribbled out this little section here, we would actually have the permutation formula. This extra component of having an additional r factorial has the effect that it gets rid of all the duplicates. You remember how we had that piece where we said, oh, there's this duplicate, and we scribbled it out for the crayon problem? There are going to be a lot of duplicates when you say the order doesn't matter. Dividing by r factorial that way eliminates all the duplicates. The interpretation, though, is still pretty similar. NCR, which is typically read N choose R, means we're taking R number of objects from a group of N, but the order they get picked in is not important. Okay, so let's continue with our crayon problem now. We would like to use the combination formula so that we can determine the total number of different choices, the total number of different groups that we were supposed to have. When we did it, we were able to create a list of 9. Did we get them all? This formula will tell us. We should recognize that in the crayon problem, there were 5 crayons to pick from. When we choose them, the order does not matter. That's why we're doing combinations, and we were picking 3. If you can read through the problem to set it up to this point, you are open. Because we know how to use the formula. The top is the first number factorial. In the denominator, we have to do a subtraction. 5 subtract 3, that's 2. If we stopped there, we would have a permutation and we would say the order is important. But the order is not important, so we have to reuse the second number with 3 factorial. Learning the formula is a big part of being able to do the formula. From here, we can expand them out. 5, 4, 3, 2, 1, 3, 2, 1, 2, 1. Looking at it, what are the pieces that will cancel? 3, 2, 1, 3, 2, 1. Well, in the numerator, 5 times 4 is 20. In the denominator, 2 times 1 is 2. So 20 divided by 2 is 10. There are 10 different combinations that we could have had, which tells us back at the beginning, we're missing one. Which one are we missing? Red, green, yellow? Yeah, that was number 9, so it's not that one. Let's consider some other options. Orange, green, red. Okay. Orange, green, red is number 4. Okay, so let's start considering yellow. Do we have yellow, red, orange? That's number 6. Do we have yellow, red, green? Yellow, red, green is number 9. Yellow, green, blue. Yellow, green, blue is 3. Yellow, orange, green. That's 5. How about red, orange, green, red, orange, blue? Do we have red, orange, blue?
Yeah.
Yep, that's number 7. Red, green. Okay.
Red, green, yellow. No.
Red, green, yellow, we have that one.
Red, green.
You can see it's a bit tricky to get some of these. Okay, so let me back this up and okay, so we'd have blue, green, orange, blue, green, red, blue, green, yellow, blue, yellow, orange, blue, yellow. Yeah, we don't have orange, blue, yellow. Thank you, Tavares. Okay, there we go. Boy. We got the boy. Yeah. The formula is not going to give us the list, but it's
We looked at 2,
supposed to have.
3.
A little bit tougher, but we got them. I would also like to point out, we did this particular one where we did it by hand. We could do, sorry, I forgot to change a word. It says permutations. This is supposed to be combinations. So let's use the combination formula for 7, choose 4. All right, so when we have 7, choose 4, what goes on top? Just the 7, the first number. Thank you, Clint. What goes in the denominator?
7 minus 4.
7 minus 4 is 3. That is always going to be there. That difference, whether it's permutations or combinations, it goes in. What's the other piece for combinations that you need? Have the 4. Getting them in the expanded format, because we were told use the combinations formula. 7, 6, 5, 4, 3, 2, 1. 4, 3, 2, 1. 3, 2, 1. Now, which pieces will cancel? We do have 4, 3, 2, 1. Those cancel. 3, 2, 1. Well, big thing worth noting, though, that Garrett noticed. 3 times 2 times 1. These 3 pieces are a 6. You put them together, you get 6. And so we could cancel the 3, 2, 1 with the 6 on top. If we choose to do it that way, what's left in the numerator? 7 times 5, which gives us our answer of 35. Yep. That is using the combination formula. We can still use the calculator to verify that this is correct. Using the calculator, we can come up to the piece, and we'll note, you see how on the bottom left we have the NCR button? That's for combinations. We have the combination button, the permutation button, and the factorial button all next to each other, so we could type in 7 NCR 4, 7 choose 4 with the parentheses, we get our answer of 35, and we know that we used the formula correctly then. We can verify the work. Just keep in mind that if it says use the formula, if you don't show the work, the natural assumption is you use the calculator, and that's not the intent behind the problem. Similar example, 6 choose 2. You should pause the video, try doing it by hand first. After you've repaused, we can continue 6 choose 2, 6 factorial, over 6 subtract 4 would be 2, and we need the other 2. Running through it, 6, 5, 4, 3, 2, 1, 2, 1, 4, 3, 2, 1.
So the 4 comes from the continuation.
We'd like to reemphasize, the 4 is coming from 6 subtract 2. Now that we have this expanded, we can cancel out all the pieces that we had. 4, 3, 2, 1, 4, 3, 2, 1. In the numerator, one way to do this is to say 6 times 5 is 30, 2 times 1 is 2, and we'd get the final answer of 15. That part in black is one way to do it. I'm going to switch colors into a red and show another way to simplify it. If we divide by the 2 from the 6, 6 is 2 times 3. So it would cancel out that 2. The only thing left in the numerator then, 3 times 5, still gives you that same answer of 15. Both methods of simplifying are completely valid. I will tell you my personal preference is the one in the red, because then I don't have to do big numbers. Especially if I'm doing something like 49 times 48 times 47. I don't want to do that. Even with a calculator, I don't want to do it. I'd rather use smaller numbers. And our last example. Suppose we have 12 teachers in our high school. And lucky us, 4 of them are going to be prom chaperones. Woo! How many different groups could you have to chaperone prom from this group of 12? Now, does it matter who's the first prom chaperone picked?
No.
Nope. Just as long as you get picked, you're still chaperoning prom. So recognizing that the order they get picked is not important, that's what tells us we have a combination problem. 12 teachers are available. 4 of them are going. So that would give us 12 factorial. 12 subtract 4 is 8 factorial. And then we'd also have the 4 as well. Writing this in its expanded format, 12 factorials, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 4, 3, 2, 1, 8, 7, 6, 5, 4, 3, 2, 1. Whew, a lot of writing. But what cancels? 8 on down will cancel. Yeah, it's like probably like 2/3 of them actually. I also can see that 4 times 3 is 12. So we can cancel the 4 times 3 with the 12 on top. In the denominator, we have 2 and 10 in the numerator. 10 is 2 times 5. So we could cancel out this other 2 from the 10. 2 cancels, and in the numerator, the only numbers that are left, 11 times 5 times 9. That number is 55 times 9. If you take 55 times 9, I think it's 505. I think that may be wrong. Let me crunch the numbers. 55 times 9, 5 carries over the 4. Yeah, that's 49. It's not 505, it's 495. I did the multiplication incorrectly in my head when I was thinking it through. But at least I was able to tell it was wrong, and we fixed it. I would like to verify this answer, though. Let's use the calculator to check to see that this all works out. We're doing 12, choose 4. Clear it. 12, combinations 4 equals 495. We know we're correct. So keep in mind from our examples, what were the learning objectives? What were we supposed to get out of this video? Do you know what a combination is? Combination is a grouping of objects where the order of the grouping does not matter. Can you use the combination formula? Both with the formula and with a calculator. And of course, the most important one of all is to be able to answer, is the order important? Answering the question, is the order important, is the deciding factor between doing a permutation problem or a combination problem.